So we are going to have a second quiz next week. Quiz number 2. November 13. November. Something wrong with next week? Is it like a compensation week? 보강 주간? November 13, Wednesday. So basically it covers the lecture 5 and 6 that I gave you through the online, and today's lecture will be the subject of the quiz number 2. It's actually good for you because once you go through the quiz problem, then it'll be much easier to prepare for the final. So lecture 5, 6, and today 7, right? So it is unfortunate that I usually I like the date for the quiz for October 13, Friday, but it never happens. Actually, it did happen once or twice. I just announced that we are going to have a quiz next week. So it will cover the previous 2 online class plus today's. So before, I think I made some introduction to you about the Fourier series last week, but on second thought, it might be better to include one more like complex integration, which is actually quite complicated, like something like this. So some more topic. And then I will, after treating this a little bit more complicated integral, then I will go back to the Fourier series. So for example, something like this. Let's say I. This is a bit complicated, right? Because you have 1 square root 1 minus x squared in the denominator. So let's consider some function hg first. Minus 1, right? So this can be written as a z plus 1, z minus 1, So let's say this is a point. So let's represent assuming the point is the xy in the xy plane. And we can say we have 2 points, -1 and +1, and say the distance from -1 to z is, say, r1. The angle between the x-axis and this straight line is θ1. On the other hand, we can put here to z as r2 and angle is θ2. And I'm going to consider 6 points. Point 1, 2, 3, 4, 5, 6. So point 1, 2, 3, 4, 5, 6, either just on the x-axis or just below x-axis. So we can think about 6 points. Point 1, 2, 3, 4, 5, 6. So 1, 2, 3 is just above the x-axis. On the other hand, 4, 5, 6 are just below the x-axis. And forget about r, just think about the angle. One, 2, 3, 4, 5, 6. So for the point 1, θ1 is, just remember that the θ1 and θ2 is the angle between x and this line. So for the θ1, for the point 1, θ1 is equal to, so actually we are measuring the angle at this point. So C, assuming the C is getting close to x-axis, and θ1 is 0, right? Because this is x-axis and this is the angle we're going to measure. The point 1 is getting close to the x-axis from the above. So θ1, for this 1 point, θ2 must be 0, and θ1 must be, θ2 must be 0, right? No, sorry about that. θ1 is 0, θ2 is 0. What happened to this point? Now, for this point, we are assuming that C is on the y-axis, and then going down toward the x-axis. Then θ1 is still 0, right? How about θ2? Hi. Exactement. So θ1, θ2 is pi. pi, right? How about this point? Here. So z is now going this way and going down. Theta 1 must be pi. Theta 2, pi. So theta 1, theta 2 is pi. How about this point 4? You're going down under the x-axis. Still pi, right? And theta 2, still pi. Point 5 is a bit tricky. Now, this point is below the x-axis. Right? Here. Theta 1 is here. Theta 1 is we have to cross this way, right? So theta 1 is 2 pi. Theta 2, here, right? Pi. So theta 1, 2 pi. Theta 2 is pi. How point 6? Point 6? 2 pi, 2 pi. So both angles are 2 pi, right? Theta 1 is 2 pi. Theta 2 is 2 pi. Right. So for this, you have to cross this x prime again, so 2 pi. From this theta 1 point of view, you have to cross here. Complete circle 2 pi. And this is actually square root of r1, r2, exponential 1 over 2 I theta 1 plus theta 2. So you still need to make a copy of this diagram. Okay, probably. So hg, z plus 1, z minus 1, square root of r1, r2, exponential I, theta 1 plus theta 2 over 2. And we have this. We have point 1, 2, 3, 4, 5, 6. So what about half angle? Point 1, 2, 3, 4, 5, 6. So for this one, theta 1, theta 2 is 0. So 1/2 theta 1 plus theta 2 is 0, right? For number 2, theta 1 is 0, theta 2 is pi, so 1/2 theta 1 plus theta 2 is pi over 2. Theta 1 is pi, theta 2 is pi, 1/2 theta 1 plus theta 2 is equal to pi. It's the same. Theta 1 is pi, theta 2 is pi, 1/2 theta 1 plus theta 2 is pi. Here theta 1 is 2 pi, theta 2 is pi, so 1/2 theta 1 plus theta 2 is 3 pi over 2. And finally, theta 1 is 2 pi, theta 2 is 2 pi, so 1/2 theta 1 plus theta 2 is 2 pi. So it looks like we have a branch cut through this line. So we can see that if you cross this x-axis, there is no phase change between 1 and 6 because 0 is same as 2 pi, right? And if you cross the x-axis from 3 to 4, still the same phase. The phase is pi to pi. On the other hand, if you cross the x-axis from 2 to 5, there is a phase change. Pi over 2 to 3 pi over 2. So this function is not singular. We have a multi-phase, multivariate function across this branch cut. So we can actually set the branch cut here. So you cannot cross this line. So branch cut is the definition of branch cut is if you cross the axis, particular axis, then there is a phase change. So from this axis, there's no change, right? In this axis, there's no change. On the other hand, from the region -1 to 1, if you cross this axis, there is a phase change. So we have to set this line as branch cut. So branch cut is definition is very simple. If you cross the axis, if you cross the line, phase change. So this is a very complicated problem, but also very straightforward and simple. If you understand how you can define the branch. So maybe this point would be most confusing, like a line. So if you have any question, probably this is the best time to ask me a question before I proceed to actually calculating the integral. You can ask me in Korean too. Or shall I explain this in Korean just in case? Okay. Let me temporarily off the record and on the record.
So can I ask something?
Yes.
Why do you define the h3 as r1 times r2 square root times e to the sum of the angles divided by 2?
Oh, I mean because we have the original integral. If you take a look at the original integral, is given in terms of this. So we like to find the method how to treat this. Right?
Yeah.
So it's clear?
Then you only formula to the square root, right?
Yeah. So actually it doesn't matter. C is square minus 1. two arc angles. So we know that we already have a pole. This will give plus minus I as a pole, right? And here, plus minus 1 is actually singular point, but it's actually end and beginning and end of the integration point. So we have to find a way that how do we apply this relativity theorem for this particular point. So if you understand this problem, then actually you are in a very good position to understand the complex integration. An amazing thing is Cauchy has done this 200 years ago. 1780 something, 200 and almost 40 years ago, Cauchy has done this integral without any computer or any calculator, just use his own pencil and paper. So this is going to be our integration. And we have two poles here, I and minus I. And of course we have a branch. So our integral will have 6. So we start with minus infinity to minus 1, C1. And from C2 integral, and 0 integral, and C3 integral, and C4 integral, and the big one. And we are going to say GZ HZ Let's do the first two integral first. C1. let's consider the C1 integral and C4 integral over GZ is some such as this. So HG can be written as this. HG exponential I theta 1 plus theta 2, right? We can represent this function as the absolute value with the base. So C1 and C4, let's consider that. And C1 is from minus infinity to minus 1 along this x-axis. So it's dx. And HZ exponential I theta 1 plus theta over 2 1 plus x squared. And C4 is from minus 1 to infinity along this way. Actually, it must be like x times 2 pi I, right? We have to. That's the same as x, right? Because C4 is below the x-axis. So we have actually like 2 pi I. But 2 pi I is equal to 1, right? So it doesn't make any difference. And HG, absolute value is the same as this. Exponential I theta 1 plus theta 2 over 2 and 1 plus x squared. Of course, it's 2 pi I squared, right? The same. But the beauty is theta 1 plus theta 2 is both pi and pi. Same angle. Just the integral direction is opposite. Minus infinity to minus 1, minus 1 to infinity. So there you have opposite value, right? So there you cancel each other. Is equal to 0, right? And as before, this small circular integral will see this point, and the big, large integral will move to 0. So I will give it as a homework, right? So you can do it as a homework that this CR, GZ, DZ goes to 0. CR, GZ, DZ goes to 0, right? So just follow the previous step we have done 3 weeks ago. That this small integral, the circular integral along this point, and big integral goes to 0. And from just dimensional analysis, because so all integral left is this and that. So if you have any questions, before I move to the next slide, next page, this is probably a good time to ask me a question again. Augustine course must be really your genius, because you figured out how to do this integral without any computational tools about more than 200 years ago. And that's the reason why you are still learning that. Even though we have a very good computer around, but still it wouldn't hurt to do just by hand. C2, C3. So any questions about the integration? All right. So now we have two integrals. Which was C2, I think. We have a branch. And we have a pole. So C2 is actually minus 1 to 1. Dx, right? So absolute value of Hg is square root 1 z square minus 1. So absolute value of z can be something like this, 1 minus x square here. So this is minus 1 to 1, square root 1 minus x square I, 1 plus x square over dx. On the other hand, C3 1 to minus 1 dx exponential 2 pi I, same as this 1 minus x square, but exponential sorry. Exponential 3 pi I over 2 is minus I, right? So dx is 1 minus 1 square root 1 minus x square minus I 1 plus x square. Oh, here minus exponential 2I 3 pi over dx. So same. So we have a minus sign and the minus sign in the integral. So we will have I over 1 minus x square over dx. Therefore, C2 over GZ, dz, C3 over GZ, dz is actually 2 over I. Maybe I should write down in the below. Equal to 2 over I. And dx. So this was the original integral that we want, called I, right? So we have 2 over I times I. Any questions? Straightforward, right? Not too difficult. So we're almost there. So can I move on to next slide? So this is the original integral. Oops. So say C. C is C1 plus C2 plus C3 plus C0 plus C4 plus CR. So this integral GZ dz is actually 2 pi I residue theta equal to pi over 2 residue theta equals 3 pi over 2, right? Is equal to 2 over I, right? So residue, we need to evaluate this. So residue theta equal pi over 2 is limit z goes to exponential pi I over 2 times z minus I gz. It's actually square root of 2, right? And here exponential I over 2. And here comes 2i. Square root of 2i over 1. How about the other residue? Residue theta is 3 pi over 2. It's actually limit z goes to exponential 3 pi I over 2 z plus I gz. It's actually same thing. Square root of 2 exponential I is 3 pi over 2 here minus 2i. The beauty is we have minus sign here and we have minus I here. So we have square root of 2 minus I minus 2i over 1. So this part actually comes from this. Z minus I, Z square, Z goes to I, is Z goes to I, Z plus I, right? 1 over 2I. And same for the second one. So this one actually explains this. So we're almost done. This integral two over I is equal to 2 pi I times square root of 2 I 2I square root of 2 minus I minus 2I. So this is 2 pi I times square root of 2 I 2I square root of 2I 2I. Because the second term we have two minus signs, so they become positive. So one of the I will cancel this I will cancel this and this, right? And this 2 will cancel this 2. So we have I square root over 2, right? Pi is equal to 2 over I. So therefore, I is minus 1 to 1 square root of 1 minus x squared 1 plus x squared over dx is equal to pi over square root of 2. So it looks like apparently this integral, which doesn't seem to have anything to do with the circle, contains pi. So it looks like if we do some complicated integral, it can be 2,000 integrals. They contain pi. So pi can be probably, I don't know, some signature left over to us. The result of the creation of this particular type of universe. And we have a particular space-time geometry, and pi can be the signature for that. So I don't know, if a different kind of universe, then this integral may be different value than pi. It could be, I don't know, like 5-dimensional space. We are basically living 3 plus 1 dimension, 4-dimensional space-time. Of course, string theory says there is another 6 more dimensions. What we feel is actually 4 dimension, right? Space-time, 1 times 3 space dimensions. That's probably the result of this. If our universe has been created differently, like we have 5 dimensions. Like, I don't know what is the 5 dimension we can feel. For space dimension is 1 pi, then this pi not be different. This integral could be different. So pi could be like a signature left to us by this current universe through the Big Bang. So you can find many integrals which contains pi. So somehow it's related to the ratio between circumference and the diameter. That's pi, right? So I don't know why this comes in, but most number of integrals gives this. So that concludes the section for this complex integral. And I think I promised in the beginning of this semester that we might have some unannounced quiz, surprise quiz. So probably this is the appropriate time. So why don't we close the door? Let's lock the door. And grab a piece of paper. This is going to be 5-point quiz. number. Piece of paper. Okay, I just changed my mind. Soon to 10 points. Number one, your name. Plus identification number. Your student number, or I don't know, passport number, or whatever. Second problem is my name. You can just write the baby down. My English name. Either way is fine. So 5 points each. So you got 10 points. Just for attending this class. You are very lucky. I will give you 2 minutes. Is enough? Two things. Write your name plus some number, your identification number, like a student identification number or serial number, or maybe passport number. Either way is fine. Some number. So we have to be able to identify you, or I don't know. All right. And my name, another 5 points. And if you have a friend, if you like to know your friends come in, you have 2 minutes. You can text your friends to come in and write down, get the 10 points. So consider this as like a bonus point. So 10 points actually is not much, but if you happen to be in the border for grade, like B plus to A, then if you happen to be at the borderline, then 10 points you should decide which grade you will be. Usually 10 points will be enough to change the grade if you happen to be in the borderline. So 1 minute left. So no more friends coming? Cheating sheet. I think you probably need 2 pages. I think 2 pages will be enough, right? And also it will cover Fourier series. Joseph Fourier was another French mathematician during the Napoleonic War. The reason for the Fourier series was during the Napoleonic War, the cannon was a very important weapon. The problem was that once in a while, the cannon itself explodes. And the soldier dies. The problem is the cannon sometimes explodes. And so Napoleon asked Fourier what's the reason. And he discovered that it's actually the weakness in the metallic structure. So he decided to analyze the periodic structure of the cannon. And so he invented a mathematical method to analyze this thermal distribution. It's called the Fourier series. So because I have covered the basics for the last week, I'll just go through some. So this is called the periodicity. Capital T. So typical periodic function is sine or cosine, right? So assuming that ft can be represented by sometimes sine like at or collection of at, then sine at plus t is supposed to be sine at. So that means at sine at plus a big T. So at must be like 2 pi n. So a can be as a 2 pi n over t, right? So the Fourier series can be represented by I'll just write it down. So ft we can represent a0 plus sum over n infinite an cosine t over 2 pi n t bn sine t over 2 pi n t. And I think I derived the formula 1 over t minus ft t over t ft dt, right? an is equal to 2 over t ft times cosine t over mt dt. Pn is equal to 2 over t ft sine t over 2 pi nt dt. So this is like right? You have to derive this as home. Most likely, I'm not going to ask for proof for this in the quiz, but you have to know this result, and you have to figure out how most likely that I designed for this problem is something like this. Say we have ft. And what is the period in this case? Right? So big T is 2. A0, if you integrate A0, what is the value? A0 is most likely 0, right? So probably you just need to calculate Bn. Most likely A0 Bn is T sine T over 2 pi n T dt, right? So actually you have done this in high school days by using the integration by part twice, right? It's one of the, like a typical example problem for 수학의 정석 or any the calculus mathematics, calculus book is one of the good examples for doing this integration. You can do it by the integration by part twice, right? I can actually give you a better method, assuming that say I is minus 1 to 2t sine at dt. Some variable a. Say a is 2 pi n over t. And if you take a look at this integral carefully, then we have sine at and we have t appears here. So actually I did figure out in high school that instead of doing integral by twice, I thought what happens if you differentiate cosine a by a? What happens? What do you get? If you differentiate cosine a by a, you get minus sine a times t, right? By chain rule. So here you say this is beta. So beta is 80. Then this integration is the same as d beta d cosine beta times dA d beta, right? is your chain rule. And you have done probably in the calculus in your freshman year. So cosine beta is minus sine beta, right? Minus sine beta and t. Minus sine at t, right? So you can say that this integration minus 1 to t sine at dt is same as minus dAd cosine at dt. Right? Same as this. If you differentiate cosine A by A, then the result is you have sine A2 with the t in front of it. So there was a exam containing this integral as one of the midterm. And instead of using the integral by part twice, I used this method and obtained the answer. But students, my teacher actually couldn't understand. And so he just crossed out my answer. Even though I got the right answer, but he said my step doesn't follow the standard rule. So that's the reason why I remember this formula, probably. And I have been using this all the time, ever since. So another potential problem is cosine A dt is same as 1 over A sine AT 1 minus 1, right? So this is 1 over A sine A minus sine minus A is 2 over A sine A. So if we differentiate this, dAd cosine AT dt is equal to dAd 2 over A sine A is cosine A 2 over A minus A squared 2 sine A, right? Twice of A분의 cosine A minus A squared sine A. So when I was a high school student, and t sine A t dt is minus dAd dt is happen to be 2 over A분의 sine A minus cosine A, right? Now set A is equal to 2 pi n over t, right? t equal to 2 pi n, right? So this is 2 over pi n over sine n pi minus cosine n pi. Sine n pi is equal to 0, right? Cosine n pi is actually minus 1 to the n. Cosine pi is equal to minus 1, right? When n equal to 1, cosine pi minus 1, n equal to 2, cosine 2 pi is equal to 1. So cosine n pi can be written as a minus 1 to the n. We have minus sign, so we have actually 2 over n pi minus 1 to the n plus 1, which is Pn, right? So for this Fourier series, we have what happened to me. So ft is actually we have 2 over t times n equal to 1 to infinite n pi over minus 1 to the n plus 1 sine n pi t. So this is my favorite too. Minus 1, 1, 2, 3. T to the 3. So in this case, the t is again 2, right? And so this is again odd function, so I guess you will get only Pn, right? And you actually do it 3 times. Differentiation 3 times. So in this case, A0, An is equal to 0. Bn will be 2 over 2 minus 1 to 1 t to the cube sine n pi t, right? tt. So this is actually, you can do this, differentiate 3 times. And then later, a equal to n pi. I will give you as a homework, because I can do that. So let me see. just for the fun of it. One over a sine at 1 to minus 1, right? So this is 2 over a sine a, right? So dAd two over minus a square sine a plus 2 over a cosine a, right? If you differentiate twice, you first differentiate it to 4 over a cube, right? Sine a minus 2 over a cosine a minus 2 over a cosine a minus a over 2 sine a. So we can combine them together as 4 over a 3 sine a. I'm not going to put them together. Sine a minus 4 over a cosine a. And you can differentiate once more, right? So copy, delete, paste. A cube over 2 sine a. Let me see, right? So if we differentiate once more, is minus 16 over a 4 sine a plus a cube 4 over cosine a plus 2 over a square sine a minus 2 over a cosine a plus 4 over a square cosine a plus 4 over a sine a. And then if you set a equal to n pi, what happens? Then this result becomes, every sine a just goes to 0, right? Only cosine term survives. 4 over n pi cube minus 1 to the n minus 2 over n pi minus 1 to the n plus 4 over n pi square minus 1 to the n. Copy, paste, and next page. So combine them together, which is, we can actually 2 over n pi, 2 over n pi square plus 2 over n pi minus 1 This is the coefficient. So Bn must be so Ft must be something like this. N equal to 1 to infinite, 2 over n pi, 2 over n pi square, 2 over n pi minus 1 to the minus 1 sine n pi t. And actually, we have to put minus sign again here. So minus. So if you have t3 times sine and you integrate, then you have, how many times you have to do this partial integration by part? 6 times, right? If you have a t square, then you have to do integration by part 4 times. Just t, you need to do integration by part twice, right? And every t you need to you have to do the integration by part twice. So this integration, actually, if you do follow the original step, then it's going to take quite a long time, because we have to do this integration by part 6 times. But this method you can get very quickly, right? So another potential quiz problem is something like this. This is also my favorite. So Ft is t square. Ft plus 2 is Ft. So probably you can do this as homework. Or maybe t to the 4 as well. So for next quiz, I think probably give you maybe two or three complex integration problem plus one Fourier series problem. So about maybe 4 problems will make you quite busy for maybe 2 hours. So I guess we have covered enough material for, probably more than enough material for next week's quiz. So I'm thinking about stopping here today. What do you think? So good luck. In English expression for good luck is like a fingers crossed. All right.